Yagi-Uda antenna is very popular in amateur radio or ham radio. It is also a common sight on housetops before the era of cable TV and satellite TV. It consists of a driven element and a variable number of parasitic elements on a boom. The driven element could be usual dipole or a folded dipole. Element behind the driven element is the reflector. Elements in front of the driven element are called directors. Typically, the reflector is longer than the driven element, while directors are progressively shorter than the driven element. Output of the radio is fed only to the driven element. Animation illustrates how a 4-element Yagi-Uda antenna works. There are 2 directors and a reflector in addition to the driven element dipole. The parasitic elements act as resonators by absorbing and re-radiating the electromagnetic waves from the driven element with a phase difference. There is constructive interference of these electromagnetic waves in the forward direction as they are in phase, and destructive interference in the reverse direction as the waves are out of phase. Net effect is a stronger signal in the forward direction and a weaker signal in the reverse direction. This is usually mentioned as the forward-backward ratio of the antenna. In the animation, the signals are color-coded similar to the antenna element for ease of recognition. Yagi-Uda antenna is often called as a beam antenna in amateur radio. Due to the size, it is less often used on HF bands than on VHF and UHF bands. The number of elements practically feasible are also lower on lower bands. They are used with antenna rotators as good directional antennas. Yagi-Uda antennas can have gains up to 20 dBi and a front-to-back ratio of up to 20 dB. Radiation pattern is linearly polarized with horizontal polarization for a horizontally mounted antenna and vertical polarization for a vertically mounted one. Bandwidth of Yagi-Uda antennas is relatively narrow, with a narrow range of frequencies within a band at which it has good gain and operable feed point impedance. The driven element or radiator can be a simple dipole with 2 quarter wavelength rods connected to either conductors of the feed line. In some versions, it is a folded dipole which has a higher impedance of around 280 ohms. The television antennas of yesteryears with folded dipole used to be fed using a twin lead transmission line with impedance of about 300 ohms. Folded dipole will need a matching for amateur radios with impedance of 50 ohms. Usual dipole has an impedance of around 70 ohms. Spacing between the elements may vary from quarter wavelength to 1/10 of a wavelength depending on the design. Radiation pattern of Yagi-Uda antenna is along the axis perpendicular to the plane of the elements towards the direction of the directors. As the parasitic elements have 0 RF voltage at the center, they can be directly attached to the boom, but this will electrically shorten them, and usually a correction in length is needed to cover this. There are versions in which all elements are insulated from the boom as well. The 2 halves of the center-fed dipole have to be insulated in the location of the boom. Many of you would have heard the term Cross Yagi in discussions among amateur radio satellite communication enthusiasts. A Cross Yagi is nothing but 2 normal Yagi-Uda antennas mounted on the same boom, rotated 90 degrees in position. Cross Yagi is used for EME, Earth-Moon-Earth, or moon-bounds, in addition to satellite communications. In all these modes, the signal has to cross the ionosphere, which can cause unpredictable polarization rotations. Circular polarization is used to reduce losses in such a scenario. Most of the antennas which radio amateurs use on HF, VHF, UHF bands have linear polarization. either vertical or horizontal, and are not ideal for satellite communications. Polarization of an antenna is the direction of electric field produced by the antenna and determines the direction of transmission and reception. In circular polarization, the radio waves rotate as the signal propagates. If it rotates to the right, it is known as right-hand circular polarization, RHCP, and if it rotates to the left, as left-hand circular polarization, LHCP. Using circularly polarized antennas helps to minimize the effects of cross-polarization losses as the satellite moves through space. Even if the satellite antenna is vertically polarized, the signal changes direction as the satellite tumbles and spins in orbit. Cross-polarization means polarization of the transmitting antenna and receiving antenna are at right angles to each other, producing great signal loss near to total in ideal conditions. If your antenna is circularly polarized, the signal loss will not be total when the satellite tumbles and spins in orbit. Difference in signals received between right and left hand circular polarization will be only 3 dB, unlike that between horizontal and vertical polarizations, which could be near total loss of signal regardless of how much power is used. Two types of arrangements of cross Yagi elements on the mast has been described. In X setup, both sets of elements are at 45 degrees to the ground so that it will look like an X. The other setup is plus or cross setup, in which the elements are at 0 degrees and 90 degrees to the ground so that they will resemble the plus sign. In the plus or cross setup, the mast must be of non-conductive material to prevent strong negative influence on the vertical elements. If both dipoles are driven by one signal with different phasing, circular polarization results. X position is usually used for circular polarization. In the plus or cross setup, it can be used as two antennas, one with horizontal polarization and another with vertical polarization. If remote switching between the positions on either limb is needed from the shack, two sets of cables have to be used. For non-switchable circular polarization, cables of different lengths united over a 3 dB coupler splitter can be used. An option for maximum flexibility is to have a polarization remote switch on the antenna. Two cables go to the antenna from remote polarization switch and one coax and a control cable go to the radio. Remote polarization switch permits switching between left or right hand circular polarization as well as between horizontal and vertical linear polarization. So multiple options are available if you use a polarization remote switch at the antenna location of a Cross Yagi. Circular polarization is produced by two linearly polarized orthogonal signals of equal amplitude which are 90 degrees out of phase. As antennas with same geometry will have same output radiation for the same input, if two linearly polarized antennas of same geometry are placed at 90 degrees to each other and fed with 90 degrees phase shifted input, output will have circular polarization. This is the principle of Cross Yagi. Phase shift of 90 degrees can be achieved by using an additional cable of quarter wavelength, taking into consideration the velocity factor of the cable as well in the calculation of quarter wavelength. Phase difference occurs due to the extra transmission time in the added cable length, one full wavelength of a sine wave being 360 degrees.